If you look through a powerful telescope at any objects in the universe surrounding you and observe that they are all moving away from you, you might decide that you have a repelling force or that space itself is expanding. Another possibility is that you are at the center of a past explosion and everything is moving away from its center. At first glance, all of these and some other explanations might seem reasonable, but scientists always talk about the expanding universe as if other alternatives are not suitable. One of the most incredible facts associated with Einstein's theory of general relativity is that it relates space-time, matter, and energy. Matter and energy dictate how space-time should curve, and space-time tells matter how to move. If we learn how all matter and energy are distributed in the universe at a certain point in time and how they are moving, we can reconstruct the curvature of space-time and the evolution over the lifetime of the universe. Observing the galaxies in the universe, we see that the gravitational dynamics of neighboring galaxies have the most influence on the closest galaxies to us. For example, the Milky Way and Andromeda are moving towards each other. Other galaxies and local groups will eventually merge as well. The rest of the galaxies are attracted to the nearest masses, large galaxies, galactic groups, and clusters. In any relatively small region of space, ranging from a few million to tens of millions of light years in size, the mass of this space determines how galaxies will move. However, on larger scales, things don't work the same way. Small-scale movements, known as regular velocities, can reach a few thousand kilometers per second, but they are overshadowed by a stronger effect that can only be seen on larger scales. This empirical observation is known as Hubble's law, which postulates that the observed recession velocity of galaxies is proportional to their distance from us. The constant of proportionality in this relationship is known as the Hubble constant. It has been measured quite accurately, and you can see its value on your screen right now. But why does this happen? In reality, why is everything moving away from each other? When Einstein introduced his theory of general relativity, he quickly realized that it had consequences he didn't quite like. A universe uniformly filled with matter would be unstable and prone to gravitational collapse. To counteract this, Einstein introduced a cosmological constant that represented a repulsive force counteracting collapse. Others understood that not accounting for this constant could lead to a non-static universe. In such a universe, the fabric of space would either expand or contract over time. Einstein's correction didn't work, and the cosmological constant led to an unstable universe. Regions with higher density would collapse, while those with lower density would expand. In a universe governed by the laws of general relativity, filled homogeneously and isotropically with matter and radiation, staticity couldn't persist. It had to expand or contract, depending on the content and quantity of the universe. And so, distant galaxies are receding from us faster the farther they are. The reason lies in the fact that a universe that adheres to the principles of relativity, isotropy, and homogeneity, while filled with matter and radiation, cannot be static. It must either expand or contract based on its content and quantity. This situation could have evolved due to various factors. Redshift fatigue. Light coming from distant galaxies loses energy as it travels through space, potentially resulting in a decrease in observed energy and a perceived redshift. High-speed motion. Rapid movement could cause the fastest galaxies to become the most distant over time. Initial explosion. An initial explosive event could push galaxies further away from us. Expansion of spacetime, the last possibility, but the one supported by a comprehensive set of data, including general relativity and the physical distribution and properties of observed galaxies. By the 1930s, it became clear that there were only two options, and the universe is indeed expanding. This was further confirmed by the fact that the redshift of objects correlated well with calculated distance and observed expansion velocity, regardless of the object's distance. But a study from 2011, represented by the red data points, provides the most compelling evidence to date that the temperature of relic radiation was higher in the past. The spectral and temperature properties of distant light confirm the fact that we live in an expanding space. Collectively, all this evidence teaches us that the universe is expanding, and most likely, this is the cause of the redshift. It's not due to motion, tired light, or the result of some explosion. Space itself is expanding. This portion of the universe we can see and study is growing over time. Since the presumed Big Bang, 13.8 billion and 8 billion years have passed, and the majority of objects whose light has reached us are now about 46 billion light-years away. As of now, the observable universe spans about 46 billion light-years in all directions from our vantage point. Beyond these boundaries, there is undoubtedly much more space, likely even infinite. Personally, I'm confident that there is more universe beyond. It's just that light hasn't had enough time to reach us. In this context, whether the universe is finite or infinite doesn't matter. It can still expand. Expanding the universe is like multiplying its size by growth factors. If it was initially finite, it will remain finite but larger in size. If it was infinite, it will stay infinite. The key point is that the universe changes, expands, and stretches. All these effects are consistent and indisputable. What lies beyond the observable universe is a topic for future videos. However, when we talk about distances in the universe, we sometimes find ourselves in a state of shock because our minds can't fathom just how immense those distances are. For example, consider a distance of 10 million light-years. But what if I tell you that the diameter of the universe is about 93 billion light-years from our perspective? The observable universe can roughly be imagined as a sphere with an observer at the center. If you were to observe in any direction, the farthest point you could see would be around 46 billion light-years away. In terms of diameter, this figure adds up to 93 billion light-years. However, if we delve into the age of the universe, this number would be much less than 93 billion. So let's try to understand today how this came to be. To answer this question, let's consider when we say that an object is at a distance of 13.8 billion light-years from Earth. What do we mean? Is it the current distance to the object? That is, how far it is now when the light from the object started traveling toward us? Or is it the distance that light has traveled? Due to the universe's expansion, these variations should differ significantly. But first, let's use a simple analogy for better visualization. Imagine two adjacent flights of stairs. You stand on one, and your friend stands lower on the other. Your friend tosses a ball to you with a certain speed. It takes some time for the ball to travel to you. If you know the ball's speed and the time it takes, you can calculate the distance to your friend. Suppose the ball travels at 10 meters per second, and you are 10 meters away from your friend. Now, let's complicate the scenario. Imagine both of you are on escalators, moving in opposite directions. Your escalator goes up, while your friend's goes down. Each escalator moves at a speed of 2.5 meters per second. Now, things become less straightforward. If your friend throws the ball at 10 meters per second, and you start 10 meters away from them, by the time the ball reaches you, you won't be 10 meters apart anymore. It would take 1 whole second for the ball to reach you, during which you'd move 17 meters away. If you were initially 10 meters apart when the ball was thrown, the moment the ball reaches you means you started at 6 meters away. It took me 0.8 seconds for this scenario. If it took exactly 1 second, it means you started at 8 meters. Now consider that I've rounded the values for simplicity. When two objects are stationary, all three values are the same. For moving objects, they're different. As you know, the universe is expanding, so things get more complicated. When we observe the distant edges of the universe, we're looking into the past. We see light from a time when objects were closer together, and the universe expanded faster in ancient times. Unlike the escalator analogy, the rate of the universe's expansion changes over time. Today, according to modern estimates, the age of our universe is around 13.8 billion years, give or take a few tens of millions of years. What does this mean for distant objects? Let's consider the current record holder, one of the farthest galaxies known to us. When we say it's located at a distance of 13.45 billion light-years, we mean the distance traveled by the light from the galaxy, whether or not it has arrived yet. For me, at least, This seems to be the most reasonable way to measure distances in an expanding universe. In the past, distances between objects were smaller. As light travels from the emitting object to our eyes, the universe continues to expand. But what does this mean for our record holder, this galaxy? Firstly, this galaxy was at a distance of 1.1 billion light-years from us when it emitted the light that has reached us today. Secondly, the light that reaches us today was emitted and sent when the universe was only 380 million years old. Thirdly, the light traveled for 13.4 billion years, and, by definition, covered that exact distance. And fourthly, now this galaxy is located at a distance of 30.3 billion light-years from us. In reality, when you read the news, watch videos, or listen to various scientists, you may not fully grasp the distances they are discussing. So, I've listed all the possible variations. However, usually the last two options are used, either the distance traveled by light or the current distance. Moreover, if the distance in light-years is less than the age of the universe, it refers to the time light traveled. If it's greater, it indicates the current actual distance. The point is, for nearby objects and objects connected by gravity, the difference between these variations is significantly smaller. Nonetheless, I would still prefer people to be more careful with their wording and to use more precise values. If each person specifies whether they mean the distance at the time of light emission, the light's journey, or the current distance to an object, confusion would be greatly reduced. This is how distances work in an expanding universe, and that colossal number, 93 billion light-years, was achieved as follows. The reason is that the accompanying distance to the farthest observable object, namely the surface of the last scattering relic radiation, is about 14 billion parsecs, or 14 megaparsecs. This corresponds to 46 billion light-years in all directions. Thus, the observable universe can be visualized as a sphere with a diameter of about 93 billion light-years, centered on the solar system, the observer's location. Since the presumed Big Bang, 13.8 billion years have passed, at least according to contemporary science. However, this time has passed for us. But since time is relative, what does it mean for observers in other parts of the universe? Does absolute time exist for the entire universe? When we say the universe is 13.8 billion years old, does this only apply to Earth, or does it hold true for the entire cosmos? So, today, let's attempt to understand this. Who knows? Perhaps someone from a neighboring galaxy is looking at us through a telescope right now, observing the dinosaurs on Earth. Furthermore, we will discuss a very unique galaxy that, so to speak, lies beyond our universe. Our Earth exists within the Milky Way, and the ages of everything we see in it match that 13.8 billion years, or almost 13.8. This age of planets, stars, and other sources of light visible in the night sky doesn't align with our own, because as you know, the speed of light is constant. For instance, if you look at a star located 200 light-years away, you're seeing it as it appeared 200 years ago. There's nothing paradoxical about this. It's negligible when compared to the 13.8 billion years. Even if we consider a star on the opposite end of a galaxy, at a distance of 100,000 light-years, the difference is practically negligible. You might wonder if there's a significant distinction between an age of 13.8 billion years and 13.8 billion 800 million years, or even the specific value of 13 billion 790 million 900,000 years. I believe the difference is inconsequential. However, if we consider other galaxies that are very distant from us, a completely different story emerges. Each point in this illustration represents a separate galaxy located at approximately 1 billion light-years from Earth. Galaxies within this structure have ages of 12 billion and 8 billion years, while the most remote galaxies are even younger. As we look farther and farther, we find galaxies that existed when the universe was less than 1 billion years old, with its age being only a small percentage of what it is today. With powerful telescopes, you could potentially see individual stars with very low heavy element content. At that time, over 99% of atoms were composed of just hydrogen and helium. Carbon, oxygen, silicon, phosphorus, iron, and other elements necessary for constructing the universe were scarce. This would result in a lack of rocky planets, organic molecules, and the chance for life. When we observe galaxies in their original state, we are essentially peering into the past. Yet, there's a crucial point to note. We aren't seeing galaxies as they are today. Rather, we are observing them from our perspective, looking into the past. For someone on a distant star or in a galaxy tens of light years away, they would see our past. If they were 100 light years away, Earth wouldn't have signs of nuclear bombs. We wouldn't have invented computers, ventured into space, or developed television broadcasts. For someone in a galaxy a billion light years away, our sun would appear younger and dimmer. Earth would only have single-celled organisms. What's even more astounding is that for observers in the most distant visible galaxies, not only would our Earth and Sun not exist, but our entire galaxy wouldn't either. We'd be a collection of large gas clouds slowly coming together into spiral arms, which would eventually give birth to our home. The oldest globular clusters, currently found in the halo of our galaxy, would also be absent. Nor would there be abundant hot young blue stars, which have vanished a billion years ago. Any of these observers on another star, in another galaxy, or even at the farthest reaches of the universe, would see a universe remarkably similar to ours, an age of 13.8 billion years. A universe where observations peer into the past in all directions, where relic radiation cooled to this temperature, and where the great cosmic web would be indistinguishable from what we see. In this universe, looking at us, they'd see us in the past, just as we see them. But doesn't all of this imply that there's some form of absolute time? Initially, it might seem so, but in reality, it's not the case. If the Big Bang truly occurred, it happened everywhere simultaneously, 13.8 billion years ago. This would be true from the perspective of any galaxy. However, what if there were galaxies moving at speeds not just hundreds or thousands of kilometers per second relative to the coordinate system of relic radiation, but hundreds of thousands of kilometers per second? This speed is very close to the speed of light. Just as time goes differently for anyone moving close to the speed of light on Earth, it doesn't matter if it's a particle, a train, or a person. Though it might seem fantastical, if a planet, star, or galaxy had been moving at speeds near the speed of light for a long time, it would appear significantly younger than the rest of the universe. Imagine that when the universe was only a billion years old, a galaxy accelerated due to a series of gravitational interactions, reaching 99% of the speed of light. Over the 12 and 8 billion years since then, this galaxy would have experienced only 18 billion years. Compared to known galaxies, it would be smaller and less spread out. Therefore, the universe must appear the same to all observers everywhere. The same amount of time should pass, and the universe should possess the same large-scale properties nearly everywhere. However, for some select observers who have spent significant time at speeds near the speed of light relative to the coordinate system of relic radiation, the universe would seem very strange. The moment they slowed down, relic radiation would appear young and the universe old. The fact that 13.8 billion years have passed since the Big Bang would apply to all and everything in the observable universe. You were moving at a speed close to the speed of light. It might be difficult to believe this. However, the conclusions I've shared are based on my perspective living on Earth, in the solar system, and within the Milky Way galaxy. All these conclusions about the age of the universe and various distances are drawn from what I see. To reach these conclusions about the age of the universe, I've studied space on the plate, then what's around me. These studies are based on my perspective. Unfortunately, not everyone is as lucky as me. Not everyone can comprehend that they're part of the universe. Now, let me explain why. For example, in this image, there's a galaxy. The name won't tell you much. You might think it's surrounded by other galaxies, but that's only from a certain perspective. If you were flying through the universe and passed near it, you'd encounter no galaxies there. As far as we know from astronomical observations, this galaxy is in complete isolation. For hundreds of millions of light years in all directions, there's nothing. The bright stars, highlighted by the fractional rays in this image, are actually in our galaxy. This ultra-distant galaxy is much larger and brighter than our Milky Way. it contains 10 times more stars. Behind it lies an even more distant background of galaxies. This background accompanies similar images taken in all directions of the Earth's sky. This galaxy is located in the Pisces constellation. The density of matter in the space surrounding it is about 1 atom per cubic meter. Unlike most galaxies, which are situated along galactic filaments, it's in cosmic voids, empty spaces between them. This galaxy is so isolated that if our Milky Way were in its place, we wouldn't have known about the existence of other galaxies until the 1960s, when powerful telescopes emerged. Now imagine where we'd be if we were at Shockey or the Hooke. The Hooke telescope, used by Edwin Hubble for his research, became operational in 1917. In the 1920s, 30s, 40s, and 50s, we wouldn't have found anything near this galaxy if we lived there. Our searches would have been halted. In that case, we might conclude that our galaxy is the only one in the universe. And indeed, it's amazing that in dark nights, the universe opens up to us. This makes you marvel at how unusual our galaxy's position in the universe is. It also highlights the incorrect assumptions we can make. Having only one point of view can make it hard to understand our true place in this universe. Similarly, a point of view about the birth of the universe can lead us astray, preventing us from truly understanding how everything came into being. Therefore, it's important to consider the universe from different perspectives. In reality, this will be a continuation of this video, and we'll talk about whether it's possible to deceive space and time, and whether it's possible, purely through scientific means, to find oneself between the past and the future, or even in the same moment of time. This illustration represents our cosmic history from the Big Bang to the present day, within the context of an expanding universe. The Big Bang was preceded by a state of cosmic inflation. However, the idea that there had to be a singularity before that is dreadfully outdated. Almost everyone has heard of the Big Bang, but if you were to ask different people, from laymen to cosmologists, to complete the sentence, "In the beginning, there was," you'd receive a multitude of different answers. One of the most common responses is a singularity, which refers to the moment when all the matter and energy of the universe were concentrated into a single point. The temperature, density, and energy would have been infinitely large. This idea could imply the infection of space and time. However, this picture is not just untrue, it's likely been outdated for about 40 years. We are quite confident that there was no singularity associated with the hot Big Bang. Space and time might not have had a moment of origin at all. Let's not rush to make hasty conclusions. Instead, let's explore what we already know on this matter and, most importantly, where this knowledge comes from. Astronomical observations conducted with various telescopes allow us to examine some of the most distant galaxies we have ever seen, many of which are at unreachable distances for us. As we look farther and farther, we discover that the most distant galaxies are moving away from us at an ever-increasing speed, thanks to the expansion of the universe. Today's universe is filled with galaxies in all directions and at various distances. On average, the farther a galaxy is from us, the faster it moves away. This is not due to the galaxies actually moving within their local cosmos. The expansion of space itself is responsible for this phenomenon. This prediction was one of the unusual results derived from the theory of general relativity by Soviet physicist Alexander Friedmann. Edwin Hubble's observations confirmed it. This means that over time, matter in the universe becomes more spread out and less dense as the volume of the universe increases. This also implies that in the past, the universe was denser, hotter, and more uniform. Extrapolating backward in time, we arrive at early, hotter, denser states. But does all of this lead to singularities where the laws of physics break down? When you extrapolate the universe's development backward in time, you start to notice several important changes. In particular, you'll reach an era where gravity didn't have enough time to form sufficiently large clumps of matter for stars and galaxies to form. Then, you'll arrive at a point where the universe was so hot that it couldn't even form neutral atoms. Beyond that, there will be a state where atomic nuclei themselves break apart. Then, you'll witness the spontaneous appearance of pairs of matter and antimatter particles, and then you'll see where individual protons and neutrons will decay into quarks and gluons. The thing is, regular physics, including the moment of the universe's beginning, breaks down in a singularity. However, achieving an infinitely hot and dense state has its consequences, many of which, unfortunately, are not confirmed by observations. Each step represents a universe that's progressively younger, smaller, denser, and hotter. Continuing this extrapolation, we see that the densities and temperatures increase to infinite values at the moment when all the matter and energy of the universe were contained in a single point, a singularity. However, the hot Big Bang, as initially thought, wasn't just a hot, dense, and expanding state. The moment when all the laws of physics ceased to work was the birth of space and time. It's a way to suddenly make the entire universe appear out of nothing. It was the original act of creation. The singularity is associated with the Big Bang, but if everything happened as described, and the universe in the past had infinitely high temperatures, there would be certain obvious signs observable even today. However, for now, let me remind you what fluctuations are. Fluctuations are oscillations, meaning any random deviation from a certain value. In the context of the Big Bang, there would be temperature fluctuations of enormous amplitudes, temperature fluctuations that would be limited by the speed of light. They would only occur on scales not larger than the cosmic horizon. Relics of high-energy cosmic materials, such as magnetic monopoles, should have remained, but temperature fluctuations don't exceed 1 part in 1,000, which is 1,000 times smaller than what the singularity-based Big Bang predicts. Fluctuations larger than the horizon have been confirmed by various satellites, but the constraints on the existence of magnetic monopoles and other relics of ultra-high energy are extremely strong. The absence of their presence has serious consequences. The universe never reached extremely high temperatures, so there must be some boundary. We can't extrapolate back infinitely far to a hot, dense state with infinitely high temperature. Moreover, there's a limitation on how far we can go while accurately describing our universe. In the early 1980s, a theory emerged that before our universe was a hot, dense, expanding, cooling, matter and radiation-filled state, it underwent a phase of inflation. The presence of a cosmic inflation phase should have meant that the universe was filled with energy inherent to space, leading to rapid expansion that stretched the universe into a flat state with uniform properties everywhere. This would have involved small amplitude quantum fluctuations at all scales. Inflation causes space to expand exponentially, which can rapidly cause initially curved or uneven space to appear flat. And even if the universe were curved, its curvature radius would be at least hundreds of times larger than what we could detect. When inflation ends, it converts the energy inherent in space itself into matter and radiation, giving rise to the hot Big Bang. However, this doesn't lead to an infinitely hot Big Bang, only one that reaches a maximum temperature hundreds of times lower than what's needed for a singularity. In other words, it leads to a hot Big Bang emerging from an inflationary state, not a singularity. The information existing in our observable part of the universe that we can measure only corresponds to the last few seconds of inflation and everything that happened after that. If you were to ask how long inflation lasted, you wouldn't naturally find an answer to that. It continued for at least a little longer than those seconds, but whether it continued a bit longer than that, significantly longer, or for an infinite amount of time, that is not just unknown, it's fundamentally impossible to know. But then, what did inflation give rise to? Many studies and discussions revolve around this topic, yet no one knows the answer because there's no evidence to rely on. There were no observations that could have been straightforwardly made. Consequently, some individuals or scientists make mistaken claims. For instance, one of the claims was that we had a theory of singularity-based Big Bang, which generated a hot, dense, expanding universe before we learned about inflation. Inflation is actually an intermediate stage, so we get the following sequence: singularity, inflation, hot Big Bang. There are numerous graphs and images created by leading cosmologists that illustrate these data, but it doesn't mean they are all accurate. They illustrate density fluctuations and gravitational waves arising after inflation. The assumption of a singularity before inflation doesn't necessarily hold. There's a very strong basis to believe that it's not the case. Mathematically, we can demonstrate the impossibility of transitioning from a singularity to an inflationary state. And that's why the space-time of inflation expands exponentially. Imagine how an exponential function works. After a certain amount of time passes, the universe doubles in size. After twice that time, it doubles again, which means it becomes 4 times larger. Wait for 3 such intervals of time, and it triples. Wait for 10 or 100 such time segments, and these doublings will make the universe 2 to the power of 10 or 2 to the power of 100 times larger. This means that if we go back in time for the same duration, or for 2, 3, 10, or 100 times longer, the universe will become smaller and smaller, but it will never reach zero. It will always be a fraction of its initial size, such as half, a quarter, an eighth, 2 to the power of minus 1/10, or 2 to the power of minus 100. No matter how far back in time we go, we'll never arrive at a singularity. The blue and red lines represent the traditional scenario of the Big Bang, where everything begins at time t equals 0, including space-time. In the inflationary scenario, represented by the yellow color, we never reach a singularity where space takes on a singular state. It could become arbitrarily small in the past, while time continues infinitely. Among cosmologists, it's well known that there's a theorem demonstrating the incompleteness of the past inflationary state. This means that all particles existing in the universe, undergoing inflation, will eventually meet when extrapolated backward in time. However, this doesn't imply that the singularity necessarily existed. Inflation simply doesn't describe everything that happened in the history of the universe, including its birth. It is also known that inflation cannot arise from a singular state, as the region undergoing inflation must always start with a finite size of space-time fluctuations on a quantum scale during inflation, which stretch across the entire universe and give rise to imperfections in density and gravitational waves. However, whether inflation emerged from a singularity or not is unknown. So every time you see a diagram, article, or history about the singularity of the Big Bang that existed before inflation, know that you are dealing with outdated scientific facts. The idea of the singularity of the Big Bang lost its relevance as soon as we understood that there was another state before the hot and dense state of the Big Bang, cosmic inflation, which likely prepared and initiated the Big Bang itself at the very beginning of space and time. Possibly, a singularity from which inflation emerged existed, but there is no guarantee. In science, there are things that can be checked, measured, predicted, confirmed, or refuted. For instance, inflation giving rise to the hot Big Bang is substantiated. Everything else is merely idle speculation. Therefore, to understand how our universe was born, it's worth considering all possible scenarios of events. If you ask any scientist if the universe has a boundary, you will likely receive an ambiguous answer, because on one hand, the universe has an end from our perspective, particularly in terms of observations. This is known as the observable universe. But if we look at science from a different angle, we understand that our universe is expanding with acceleration, thus there cannot be any limitations. You will get approximately this answer, but only with detailed arguments, formulas, and explanations of why everything is the way it is in this world. It's known that due to the expansion of the universe, there exists an event horizon beyond which we cannot penetrate. We are witnesses to the fact that there is at least one intelligent life form. Believing whether we are alone or if there is someone else out there is a personal matter for each individual. However, let's imagine that in a distant galaxy there is another civilization, and naturally the event horizon for them is of the same size. And from their point of view, they could observe those parts of the universe that are beyond our horizon. Roughly speaking, they know what is unknown to us. Let's assume that an interesting cosmic phenomenon or a unique galaxy they observed astounded them so much that they wanted to tell us about it. With the help of some mega-advanced and unique future technologies, we receive their signal with this information. In that case, we would learn what lies beyond our event horizon. What do you think? Is this theoretically possible without violating the modern and known laws of physics up to 2019? So let's delve into all this in more detail. On one hand, we can trace the universe's history back to its very beginning, to the Big Bang 12 and 8 billion years ago. We have this magnificent image of the universe captured using background radiation. We can also observe stars and galaxies that formed during that time within the reach of modern telescopes. At the moment, the record is held by light that traveled to us for 13.7 billion years from an object currently 33 billion light years away. Only the most advanced telescope could surpass this record. But the essence is that our observations are limited to the observable part of the universe since the moment of the Big Bang. Light traveled 13.8 billion years, meaning we can only see the light that traveled that many years in any direction. However, this doesn't mean there's no universe beyond this border. We're sure it's there. After all, light still reaches us, and the question is about how much of it is there. And here, our experiment begins. If there's a limitation on what can be seen, then this limitation also applies to those observers whose light is visible differently. In other words, if we take two galaxies situated on opposite sides of us, and the light from them traveled 13.7 billion years, we can see both of them, but they won't see each other. If each of them has intelligent beings, couldn't they send us information about what they see, which is unavailable to us? Could they thus deceive the limitations of space-time and provide us with information about the part of the universe we can't see? Or could we send them images of the faraway galaxies captured by the Hubble extreme, or even a map of the universe as we see it? If we continue exchanging this information, would each participant eventually know more than they can see with their own eyes? However, there's a catch. Let's remember light from a very distant object. The thing is, that light would be old. If we see something whose light traveled to us for 12.4 billion years, and the object is now 33 billion light years away, we see it as it was 400 million years after its creation. Of course, it's a distant galaxy and is still emitting light, but we'll never receive it. The universe isn't just expanding, the expansion is accelerating, and this is a firmly observed fact. The question is why it's accelerating. The biggest explanation for this is dark energy. We'll talk about that later, at least explaining what's generally understood as dark energy. So the light emitted by galaxies beyond certain limits will never reach us. If it weren't for dark energy, we would eventually see it and receive the information they sent, but only after the light emitted by those galaxies reached us. Therefore, we can get information from objects beyond our horizon, but only after they move inside our horizon. And due to dark energy, whatever gets inside our horizon is already gone. This viewpoint is examined from one perspective, taking into account the theory of the Big Bang as the beginning of the universe, and nothing prevents us from discussing it in a few episodes. If our eyes were sensitive gods, and if the radiation was not absorbed by the atmosphere, the sky above us would seem more interesting than it is now. Every day, you would notice bright flashes that somehow appear at any point in the sky and quickly disappear. Some flashes would be so bright that they would momentarily overshadow everything, even the sun. Perhaps it would be challenging for us to get used to such occurrences, but this is what gamma astronomy has been observing for decades. Gamma flashes are the most powerful things ever seen in the universe, and they occur constantly. Nothing in our galaxy shining more intensely than this event, and it lasts only a few seconds. It emits as much energy in that short time as the sun generates during its 10 billion year lifespan. Of course, scientists are trying to explain the source of such energy, but as often happens, many questions remain unanswered. An unexpected discovery. Long before the first gamma rays of cosmic origin reached our detectors, scientists knew that the universe must produce them. Within various processes, the interaction of cosmic rays with interstellar gas was expected to generate bursts of radiation, including in the gamma range. Therefore, studying the universe in this wavelength was considered a promising branch of astronomy in the first half of the 20th century. However, it was challenging to expect the development of gamma astronomy on the Earth's surface, since our beautiful atmosphere absorbs radiation of such wavelengths. So the first gamma photons of extraterrestrial origin were discovered by astronomers with the advent of the space era in the early 1960s. NASA launched the first gamma telescope, Explorer 11, into low Earth orbit, which managed to detect fewer than 100 gamma radiation photons originating from astrophysical sources. However, no one expected to see what was accidentally discovered, not even through scientific equipment designed for such purposes. The thing is, gamma radiation is also a product of nuclear bomb explosions. Therefore, in the late 1960s, the USA launched a series of Vela satellites into orbit to detect similar bursts. Americans suspected that the Soviets would conduct secret tests of their bombs, despite having signed a treaty banning such experiments. As it turned out, on July 2, 1967, the first burst did indeed appear, but its nature was challenging to explain through any nuclear weapon signature. Furthermore, more Vela satellites recorded an increasing number of bursts, which led to the need for a team of scientists from the research laboratory in Los Alamos to investigate their origins. The team managed to identify the origin of at least 16 bursts, which turned out to have no connection to Earth or the Sun. Through meticulous research and verification, their findings were published in the Astrophysical Journal in 1973 in an article titled Observations of Gamma-Ray Bursts of Cosmic Origin. This marked the beginning of the gamma-ray burst era and hundreds of subsequent studies attempting to explain their nature. Early speculations about the nature of the bursts involved two main camps among scientists. Some believed that the bursts originated from the outskirts of the Milky Way, while others preferred cosmological explanations, suggesting that the sources of radiation could be located deep in space. However, it was only in 1991, with the launch of the Compton Gamma Ray Observatory, that it became clear that the bursts are evenly distributed in all directions. This argument goes against the idea that the sources originate from our galaxy because they would likely be concentrated in the galactic plane, or at least near it. Instead, the bursts occur everywhere, and each time in a new location, appearing unexpectedly and disappearing rapidly. The duration of the bursts varies from just fractions of a second to several minutes, with a typical burst lasting only a few seconds. This is remarkably fast, even in the context of our familiar life, and in the timescale of the cosmos, it is minuscule. Some scientists suspected that the rapid temporal variability indicated that the sources of the bursts must be compact and emitting jets that move at speeds close to the speed of light. It was logical to assume that such jets would interact with the interstellar materials surrounding them, creating shock waves. This might appear like a gamma-ray burst's afterglow, but in the form of lower energy emissions, such as X-rays, ultraviolet, and optical radiation, as well as on longer wavelengths. If astronomers could observe this afterglow, they might be able to understand more about the origin of the bursts and their distances. However, the early searches for afterglows were unsuccessful because the next burst could occur anywhere, and it was challenging to quickly point any other telescope sensitive to shorter wavelengths in that direction. Such a telescope is known as a satellite, and it was the satellite that succeeded where others failed. In 1997, it detected the gamma-ray burst GRB 970228. However, apart from the gamma-ray detectors on board, it also had a camera that could see in X-rays. This camera was the first to capture the fading afterglow that lasted for several days after the initial burst. Subsequently, with the help of ground-based telescopes, astronomers were able to identify a very faint galaxy where the afterglow was observed. Unfortunately, due to its low brightness, it took several more years to precisely determine the distance to this galaxy. Nevertheless, the discovery of another gamma-ray burst registered by the satellite in Timashka was a true breakthrough. Finally, it became possible to measure the redshift of the object that could be the host galaxy of this burst. It turned out that the burst had traveled to us for approximately 6 billion years, indicating that it indeed occurred in a very distant and ancient galaxy. Taking this colossal distance and the brightness of the bursts into account, astronomers finally understood the tremendous energy they deal with. The most powerful short-duration bursts surpass the brightness of an ordinary supernova by hundreds of times. In fact, their average brightness at such vast distances is comparable to a star within the Milky Way. However, the condition is that the source of the burst is billions of light-years away from Earth. As I mentioned earlier, a typical gamma-ray burst emits as much energy in a few seconds as the Sun produces during its entire 10-billion-year lifespan. This energy is highly focused, allowing us to observe only those bursts that are directed squarely at us. On average, astronomers observe approximately one burst per day, but according to their calculations, about 500 similar explosions do not reach our detectors during the same period. This raises the question of the source of these long-duration energetic events, which remains a challenging topic. If we examine the curves around these phenomena, they appear quite different, much like the fingers of deputies. Seemingly, no two gamma-ray bursts are alike. Some curves seem chaotic, with erratic jumps in brightness, while others begin as a small flash, which seems like a precursor to the appearance of another, more powerful burst that emerges after a few seconds. Nevertheless, gamma-ray bursts do have at least one characteristic that astronomers use to classify them: their duration. So-called long bursts are more prevalent and last from 2 seconds to several minutes, while short bursts have durations of less than 2 seconds and often vanish within milliseconds after their appearance. Long bursts are better studied since they make up about 70% of all known bursts. Their longer duration allows astronomers to point other telescopes towards the burst's location for follow-up observations after the initial flash. This helps in searching for the afterglow and potential galaxies from which the burst likely originated. Typically, the bursts come from galaxies that are very young and undergoing intense star formation. These galaxies serve as ideal places for the birth of massive stars, which are known to explode exceptionally powerfully. In many cases, astronomers have found supernovae in the same location shortly after gamma-ray bursts, and this correlation is difficult to attribute to mere coincidence. For example, supernova SN 1987A appeared after one such gamma-ray burst, signaling the first hint that these two most extraordinary explosions in nature might be connected. However, the energy released during a gamma-ray burst is so immense that it is essentially equivalent to the transformation of the entire mass of the Sun into pure energy within seconds. A typical supernova would hardly be capable of accomplishing such a task. To explain these bursts, something more powerful is needed, such as a hypernova. These explosions are about 100 times brighter than supernovae and are thought to be produced by extremely massive stars rotating at exceptionally high speeds with strong magnetic fields. When a star is at least 30 times more massive than the Sun, it burns through its hydrogen reserves until it can no longer withstand its own gravitational force, causing its core to collapse. It then forms a black hole, losing its core in the process. The star begins to fall into the black hole with all its material, and the black hole gladly devours it. However, in stars that rotate exceptionally fast, the material falling into the black hole swirls around it at tremendous speeds, like a frenzied vortex. Inside the star that is about to die, a black hole with an accretion disk emerges. Overheated plasma is trapped in the magnetic fields, which twist it into jet-like streams resembling an electromagnetic cannon. These streams of gas break through the hapless star's poles and shoot out into space, draining the star and forcing the plasma flows to move in narrow jets that tightly focus the energy. If these jets are precisely directed towards the Earth, we observe this energy release in the form of a burst. However, if the burst is directed in any other direction, the gamma-ray burst will remain undetected. This model of a massive star's core collapse is currently the most accepted explanation for generating gamma-ray bursts. However, it only explains the sources of long-duration bursts. Explaining the sources of short-duration bursts is much more challenging. This is mainly due to their rapid and brief nature, ranging from a few milliseconds to 2 seconds. It is known that short bursts are usually dimmer by a factor of 10 than long bursts, but they emit higher energy gamma-ray radiation. This suggests a different nature for their source. Before 2005, no afterglows of short bursts were detected, earning them the name dark bursts, as they left no afterglow. However, everything changed with the launch of NASA's Swift gamma-ray burst mission, possibly one of the most successful space missions ever. Swift, in general, has been one of the most successful space missions launched. PAS was launched back in 2004, and it has been operational for 19 years now. Besides its highly sensitive gamma-ray detectors, the observatory is equipped with X-ray and optical telescopes that can automatically and swiftly turn towards a new gamma-ray burst and study it after the burst. Currently, SWIFT works in conjunction with another space gamma-ray telescope, Fermi, launched in 2008. By the way, the animation of gamma-ray activity in the sky, captured by Fermi over the past year, shows that most of the purple dots are emissions from blazars, also known as quasars, which are jets pointing directly towards us. The yellow spot represents the sun moving across the sky during this year. Thanks to the work of these telescopes, astronomers have finally managed to observe that at least some short-duration gamma-ray bursts have an afterglow that quickly fades away. They have also been able to localize the sources of their origin, and some of them were found not to be associated with regions of active star formation. For instance, the gamma-ray burst on May 5, 2009 was found to originate from elliptical galaxies where star formation practically does not occur, and stars in such galaxies are mainly old and less massive, not prone to exploding as supernovae. However, this aligns with the popular idea among scientists that short bursts do not originate from massive star explosions, but from the collision of two neutron stars, or a black hole and a neutron star. Confirmation of this idea was captured by the Hubble Space Telescope when it managed to detect the flash of a so-called kilonova immediately after SWIFT detected another short gamma-ray burst. A kilonova is a powerful explosion resulting from the collision of neutron stars or black holes with similar stars, thus supporting the connection between gamma-ray bursts and neutron stars. This link was further strengthened by observations from the LIGO Observatory, which specializes in studying gravitational waves. In 2017, LIGO detected a series of gravitational waves caused by the merger of neutron stars, providing even more reliable evidence for this connection. Interestingly, at the same time, the Fermi Gamma-Ray Space Telescope recorded a short gamma-ray burst in that part of space. It appears that the remnants of neutron stars after a collision rotate around the newly formed black hole, similar to what is observed in the model of long-duration gamma-ray bursts. The rapid rotation of matter in the accretion disk also generates powerful short gamma-ray bursts. Moreover, last year, two independent groups of astronomers observed evidence of a kilonova immediately after a long-duration gamma-ray burst, suggesting that this type of gamma-ray burst may also be caused by neutron stars. Overall, this indicates that we still do not fully understand the nature of the most powerful explosions in the universe. Now let's finally talk about the most powerful burst in the history of observations, the record holder for the brightest flash ever observed. This event, named GRB 22109, occurred on October 9, 2022. The burst was so intense that it was immediately dubbed the brightest of all time. It lasted quite a long time, about 7 minutes, and was so bright that it overwhelmed most gamma-ray instruments in space, making it challenging to determine its actual intensity. Eventually, American scientists had to reconstruct this information using data from the Fermi telescope. By comparing the emission from GRB 22109 with the previous record holder that occurred in 2013, they found a colossal difference in brightness. Analyzing this burst and comparing it with thousands of previous ones, scientists concluded that such an event happens approximately once every 10,000 years. Thus, this energy burst is likely the most powerful in the history of our civilization since records began. After the burst, it was incredibly bright, and numerous observatories worldwide observed it. Astronomers were expecting to witness a kilonova associated with the burst, but so far they have been unsuccessful in finding it. One possible reason for this is that the burst occurred very close to the plane of our galaxy, so dust clouds may simply obstruct the light from reaching us. As a result, astronomers hope to see it using James Webb Space Telescope, which can see through clouds in the infrared range of the electromagnetic spectrum. Interestingly, when the radiation travels through our galaxy, including through gas and dust clouds, it scatters, creating X-ray reflections. In the X-ray range, this looks like expanding rings from the location of the gamma-ray burst. The European Space Agency's Newton X-ray telescope has detected around 20 such rings, each formed by a separate cloud of gas and dust. According to NASA's article, the way X-ray radiation scatters depends, in part, on the distance to these clouds. The widest ring in this image comes from a cloud about 13,000 light-years away, and the inner ring comes from a cloud at a distance of 61,000 light-years, which is from the other side of our galaxy. By the way, this is only the 7th gamma-ray burst that shows X-ray rings, and the number of these rings is 3 times greater than what was previously observed. Is there a threat to Earth? Unlike most gamma-ray bursts observed in very distant galaxies, the latest record holder is perhaps an exception. It occurred at a distance of approximately 2 billion light-years from us. That's still very far away. However, could something similar happen in our galaxy? But it's better if they continue happening in galaxies billions of light-years away from us. If something similar were to happen relatively close, the intense radiation, at the very least, could deplete our ozone layer, leading to catastrophic problems associated with harsh ultraviolet radiation from the sun. That's why the idea that the Ordovician Silurian extinction could have been caused by a gamma-ray burst around 450 million years ago is so popular. However, in reality, there is not substantial evidence supporting this hypothesis. Most paleontologists will tell you that this extinction is more likely related to climate changes on the planet or a reduction in oxygen levels in the oceans due to geological processes. So, even if a gamma-ray burst were to occur someday in our galaxy, the question remains open. Moreover, all known gamma-ray bursts originate from ancient, metal-poor galaxies, and it is uncertain whether modern, metal-rich galaxies, like the Milky Way, can produce such explosions. Even if they could, the likelihood of the gamma-ray bursts hitting Earth directly seems almost impossible to me and some others in the world, despite the occasional internet scare. Stars, planets, and cosmic matter, bound together by gravitational forces, form some of the most massive objects in the universe, galaxies. The exact number of galaxies remains unknown, but it is estimated to be several hundred billion, and that's only within the observable part of the universe. Despite galaxies being astronomically distant from one another, they sometimes collide. Such collisions are truly spectacular events on a grand scale. Cosmic evolution. In the universe, there are galaxies orbiting around a common center of mass. In such systems, there's a central giant galaxy with several satellite objects. During their evolution, if the orbits of smaller galaxies do not match, they all start to revolve around this center. However, if galaxies have identical orbits, they will merge into one large system, while the smaller object gets torn apart. Astronomers observe such collisions quite frequently. It is believed that the Andromeda galaxy also collided with a smaller galaxy in the distant past. Similarly, our system has also absorbed smaller galaxies. But if astrophysicists claim that the universe is expanding, why do galaxies collide? And all because the expansion of the universe is happening slowly. Galaxies in clusters and superclusters experience gravitational attraction towards each other and move at speeds of hundreds of kilometers per second. The cosmological expansion reaches such magnitudes only at distances of tens of millions of light-years, which is hundreds of times larger than the sizes of galaxies. Therefore, within clusters, galaxies do not notice the expansion of the universe. They move and collide as if it doesn't exist. However, no matter how common such interactions may be, astronomers rarely manage to capture dynamic images of colliding galaxies, like the ones Hubble captured. ARC 282 consists of the spiral galaxy NG69 and its smaller companion, IC 1559. They both have highly active cores, serving as powerful sources of radiation. The activity of ARC 282 is associated with the black holes located at their centers. Tidal interaction processes have led to a redistribution of matter within the galaxies, providing the black holes with abundant food. The galaxies have also formed a connecting bridge, which is visible in the Hubble image, consisting of elongated gas and dust affected by tidal forces. And that's not all. The Hubble Space Telescope also took a series of photos of two merging galaxies in the VV689 system, which astronomers have named the Angel's Wings. Unlike random visual alignments of galaxies that only appear to interact from Earth's perspective, these two galaxies in VV689 are in the midst of a collision. This galactic interaction has made the VV689 system in the constellation Leo nearly symmetrical, and now they resemble huge galactic wings. Another well-known space telescope, the James Webb, also captured interesting images. The star cluster in the Cartwheel Galaxy was formed as a result of a collision with a satellite galaxy. The Cartwheel Galaxy has two rings that expand outward from the collision center, much like ripples in a pond after a stone is thrown in. Due to these distinctive features, astronomers refer to it as a ring galaxy. It has a less common structure compared to spiral galaxies like the Milky Way. In the next two galaxies shown in the cosmic image, they passed through each other, leaving a bridge of young blue stars between them. The head-on collision between the two galaxies showcased an object of triangular shape where thousands of stars were born. This image was captured by the Hubble Space Telescope, as reported by NanoWork. Astronomers speculate that the galaxies passed through each other, triggering a fiery burst of star formation in a unique shape in NGC 2445, where thousands of stars ignite. This galaxy is rich in gas, the fuel from which stars are created, leading to its star-forming abundance. However, the new galaxy has not managed to escape the gravitational grip of its partner, NGC 24. The galaxy has pulled gas from NGC 2445, creating the peculiar triangle of newly formed stars. As we can see, these interactions can appear stunningly beautiful. In the search for dark matter, but it is not only the beauty that fuels scientists' curiosity. As early as the 1970s, serious arguments emerged in favor of the idea that galaxies contain so-called dark halos, apart from stars and gas. Theoretical arguments arose from considerations of the stability of the stellar disks of spiral galaxies, while observational evidence came from the large, non-decreasing rotation velocities of gas at the far edges of galactic disks, where there are almost no stars, and therefore the rotation speed is determined through gas observations. If the entire mass of a galaxy was primarily contained in stars, then the orbital velocities of gas clouds located beyond the stellar disk would decrease as the distance increased. This is observed in the planets within the solar system, where the mass is primarily concentrated in the Sun. However, in galaxies, this is often not the case, which indicates the presence of some additional massive and extended component whose gravitational field imparts high velocities to the gas clouds. The situation was partly clarified when massive dark halos were introduced into the mathematical model of galaxies. These dark halos do not contribute to the galaxy's overall luminosity and are only evident through their gravitational influence on the stellar subsystem. One way to obtain information about the structure of dark halos is by studying extended structures that form around galaxies during their interactions. For example, sometimes, during a close passage, one galaxy steals gas from another, winding it around itself in the form of an extended ring. The existence of extended polar rings can only be explained if the mass of the dark halo is approximately twice that of the luminous matter in the galaxy. Tidal tails also serve as reliable indicators of the presence of dark matter in the peripheral regions of galaxies. Perhaps the first evidence of hidden mass was obtained as early as 1933, when the astrophysicist Fritz Zwicky noticed that galaxies in the Coma cluster were moving faster than expected, implying the presence of some invisible mass that kept them from flying apart. The nature of dark matter remains unknown, so it is often referred to as some abstract cold dark substance that interacts with ordinary matter solely through gravity. However, due to its significant mass, it acts as the active background on which all scenarios of structure formation and growth in the universe unfold, while ordinary matter passively follows the proposed scenario. These ideas form the basis of the so-called hierarchical clustering scenario. According to this scenario, primary density fluctuations of dark matter arise due to gravitational instability in the early universe and then multiply by merging with each other. As a result, numerous gravitationally bound dark halos are formed, differing in mass and angular momentum. Gas collapses into the gravitational wells of these dark halos. This process is called accretion, leading to the formation of galaxies. The history of mergers and accretion of each dark matter clump largely determines the type of galaxy that emerges within it. The appeal of the hierarchical clustering scenario is that it describes the large-scale distribution of galaxies quite well. The most impressive numerical experiment conducted within this scenario is called the Millennium Simulation. Astronomers reported its results in 2005. In the experiment, the n-body problem was solved for 10 billion dark matter particles, starting from when the universe was only 120 million years old until the present day. During this time, nearly half of the dark matter had gathered into dark halos of various sizes, totaling about 18 million. Although complete and unequivocal agreement with the observations of large-scale structure has not been achieved yet, there is still much to discover. In 2002, a team of researchers led by Beth Willman began the search for unknown satellites of the Milky Way in the Sloan Digital Sky Survey. The first success came in March 2005, when a dwarf spheroidal galaxy was discovered at a distance of 300,000 light-years from us in the constellation Ursa Major. It became the 13th satellite of the Milky Way, with a record-low luminosity. All its stars emit light comparable to that of a single supergiant star, such as Deneb, the brightest star in the constellation Cygnus. The year 2006 turned out to be exceptionally fruitful for the discovery of satellites of our galaxy, when two other teams of researchers discovered 7 dwarf spheroidal galaxies around the Milky Way. And apparently, this is not the limit. Only recently, astronomers started to discover galaxies entirely devoid of dark matter or containing it in extremely negligible amounts. For example, the dwarf galaxy NGC 1052 DF2, which was discovered a couple of years ago by a team led by Peter van Dokkum from Yale University. Since then, several similar objects have been found, including DF4, located near DF2. These galaxies greatly puzzle scientists who are trying to understand how they could have formed without dark matter, or how they lost it. One hypothesis links their appearance to galactic collisions. In such an accident, the masses of their dark matter can continue their trajectory, passing through each other. However, clouds of ordinary matter experience pressure from each other, slow down, interact, and separate from the dark matter. This scenario is supported by an article published in the journal Nature by Van Dokkum and his colleagues. Observations of DF2 and DF4 showed that the trajectories of these galaxies started to diverge from a common point about 8 billion years ago. Moreover, other dark matter-poor dwarf galaxies also started moving along with them. Today, DF2 and DF4 are part of a chain of about 7 to 11 such objects, that located at a distance of about 70 million light-years from us. On the scale of star clusters, dwarf galaxies, and galaxies, collisions and mergers are constantly happening. Even our Milky Way is currently disrupting the Sagittarius dwarf spheroidal galaxy, which is its satellite. And in the future, this relatively small cosmic body, with only 1% of our galaxy's mass, will be completely absorbed. Looking further into the future, we can expect a collision and merger with the large Andromeda galaxy. According to scientists' predictions, the Milky Way and the Andromeda galaxy will collide in about 4.5 billion years, and quite soon, in 3 billion years, Andromeda will approach us so closely that the stars of its galaxy will be visible to the naked eye. What will this collision look like? Thanks to the Hubble telescope's image, we can now visualize what the merger of the Milky Way and Andromeda will look like from the outside. A group of 3 galaxies, collectively named NGC 7764A and located in the Phoenix constellation at a distance of 425 million light-years from Earth, serves as a model for this scenario. Scientists are already running simulations of the collision between the Milky Way and the Andromeda Nebula on supercomputers. Data indicates that the Milky Way has absorbed smaller neighbors in the past. For example, some dwarf galaxies and globular star clusters were destroyed by tidal forces and transformed into star streams, with their stars likely to be eventually absorbed by our galaxy. Using data from the Gaia Space Telescope, scientists partially answered the question of when the last collision and absorption of a neighbor occurred. Gaia creates a 3-dimensional map of the galaxy by measuring distances to stars, enabling scientists to observe their movement directions. This led to the discovery that around 8 to 10 billion years ago, the Milky Way engulfed a sizable dwarf galaxy called Gaia Sausage Enceladus, GSE. As an inheritance from the collision, we received about 8 new globular star clusters along with 50 billion new stars. Additional research revealed that GSE was not a satellite of our galaxy, but was moving in a direction opposite to the Milky Way's rotation. Thus, our courses intersected and a collision occurred, rather than a gradual merger. This intergalactic catastrophe provided us with material, forming about 50% of today's halo and 20% of the dark matter halo. The next similar event, as we mentioned before, will be the encounter with Andromeda. Scientists speculate that if the Andromeda Nebula and the Milky Way eventually merge, the resulting new galaxy will have an elliptical shape. It is even given a name, Milkomeda. By that time, the Sun, which might have transformed into a red giant, will be relatively far from the galactic center since the distance between stars will increase. However, this won't impact us anymore. Absolutely all galaxies, except for our own, are extremely distant astronomical objects. We will never truly know what happens in these immense gravitationally bound systems and the stars within them. Unfortunately, I will never have the chance to visit them. We can't send an umbrella or any device there. We won't know if there is life or wondrous forms of life. The universe, unfortunately, has taken away that possibility from us because colossal distances separate us. Galaxies are scattered throughout the entire universe. Nevertheless, we are grateful since one of these galaxies once gave us life, and now we observe them since time immemorial. Each of the galaxies is currently living its own life cycle. They collide, merge with others, evolve in their unique way, die, and are reborn. Each of them is distinct and peculiar. Almost everything you know about objects in the universe, planets, stars, moons, nebulae, is located within galaxies. They have become a peculiar haven for everything. To start, it's worth noting that the number of galaxies in the observable universe is genuinely unknown. However, with the naked eye, we can see 4 whole galaxies in the sky. They are the Andromeda Galaxy, the Large and Small Magellanic Clouds, and the M33 Galaxy in the Triangulum constellation. But despite being able to see the contours of galaxies clearly in the sky or in photographs, in reality, galaxies do not have clear boundaries. It is not possible to precisely determine where the galaxy ends and intergalactic space begins. In the optical range, a galaxy may appear to have a certain size, but when measured using radio observations of interstellar gas, its radius can turn out to be much larger, and this is not uncommon. Typically, the size of a galaxy is understood as the photometric size, which is represented as a certain curve on its illuminated surface, connecting points of equal brightness. The measured mass of a galaxy will depend on its size. Firstly, there is the core. The core is a small region at the center of the galaxy. When we talk about galaxy cores, we often refer to active galactic nuclei, where processes cannot be explained by the properties of stars concentrated in them. In such cores, processes occur that release an enormous amount of energy. Common signs of activity in these cores include the ejection of ionized gas or high-powered radio emission, though not always. Often, the unusual behavior of active galactic nuclei is associated with supermassive black holes, and currently, this is the most widely accepted theory. The second component is the galactic disk. The galactic disk is a relatively thin layer where most of the galaxy's objects are found. It is a component in the lens of visible and spiral galaxies containing spiral arms. The disk predominantly contains younger stars compared to the galactic bulge, and their motion is well ordered. They revolve around the center of the galaxy in nearly circular orbits lying in the same plane. Galaxies have a high density compared to their surrounding physical components, like the halo or bulge, which are populated with older stars. In the disks of galaxies, often, spiral arms can be observed, radiating from the center of the galaxy, where the density of interstellar gas and young stars is particularly high. It is within such a spiral arm that we live. Next, let's talk about the so-called galactic halo, a term used in astrophysics. The galactic halo is an invisible component of a galaxy and is hypothetical in nature. Essentially, The galactic halo is the outermost part of the galaxy that greatly interests scientists, as studying it can help understand where the gravitational influence of one galaxy ends and another begins. Another galactic component is quite rare and is known as the polar ring. For example, the galaxy NGC 465a has this component. In the classical case, a galaxy with a polar ring has two disks rotating in perpendicular planes, with the centers of these disks coinciding. However, the exact cause of the formation of polar rings remains incompletely understood. Galaxies with polar rings are a type of galaxies where an outer ring of gas and stars rotates over the poles, and these polar rings are believed to form when two galaxies interact gravitationally with each other. The next galactic component is called the bulge. It is a central bright elliptical component of spiral and lens-shaped galaxies. It mainly consists of old stars moving on elongated orbits. The typical population of the bulge includes red giants, red dwarfs, or supernova, two types, as well as variable stars like Cepheids or globular clusters. For example, in typical lens-shaped galaxies, the bulge is larger relative to the galaxy's diameter compared to spiral galaxies. In my opinion, the bulge is one of the most interesting elements in the structure of galaxies. Now let's talk about the bar, or in layman's terms, the bridge. It looks like a dense and elongated formation consisting of stars and interstellar gas. It serves as the primary supplier of interstellar gas to the center of the galaxy. With this knowledge of the necessary components, we can now move on to classifying galaxies and learn more about these stellar islands. There are different classifications of galaxies, such as the Hubble classification or classifications based on infrared telescopes. Elliptical galaxies. Approximately 25% of all known galaxies are of this type. They are highly luminous and, from a distance, appear like giant shining spheres with the highest brightness at the center and fading towards the edges. Elliptical galaxies are nearly entirely composed of old stars, giving them a yellow or reddish hue. New stars are almost not formed in them, since the amount of interstellar gas and dust in them is negligible, although there are occasional exceptions. Elliptical stellar systems differ only in size and compression. They are classified based on their compression with letters E from 0 to 7. This number corresponds to the degree of flattening of the system. For example, E0 would be a spherical cluster, while E6 would be much more flattened. Moreover, according to the classification, an E0 galaxy can be perfectly round, while an E7 galaxy can be oval-shaped. The star formation in galaxies of this type has ceased for several billion years, and there is hardly any cold gas or cosmic dust left. Most massive galaxies are filled with very sparse hot gas with temperatures over 1 million kelvins. On the other hand, in spiral galaxies, star formation occurs more uniformly. Therefore, the most massive stars in elliptical galaxies have long completed their existence, while in spiral galaxies, new stars are constantly being formed and observed. One of the most common examples of an elliptical galaxy is M87. Spiral galaxies are the most widespread type and probably the most beautiful. They constitute more than half of all known galaxies. A spiral galaxy appears as a disk with a bright yellow ball in the center, around which spiral arms are coiled. These arms consist of fainter branches with a bluish tint due to the presence of specific stars, such as white and blue supergiants. In contrast to elliptical stellar systems, they possess several distinctive structural features. Spiral galaxies have spiral arms where active star formation processes occur. They have a stellar disk, which is a relatively thin layer of matter along the galaxy's plane, where the main mass of objects in the system and stars is located. Stars within the disk rotate around the center of the galaxy. In spiral galaxies, the presence of interstellar gas and dust, essential for star formation, is widely observed. Many spiral galaxies have a peculiar structure at their center known as a bar, from which the spiral arms extend. They are classified with the letter S and differ in the density of arm placement. Typically, these galaxies have 2 or 3 arms, although in some cases, the arms may vary in size. All of these arms, unless influenced by galactic collisions, are coiled in the same direction around the center of the galaxy, where most of the matter is concentrated, such as a supermassive black hole and dense spherical clusters of old stars, known as bulge. For instance, our own galaxy, the Milky Way, and the Andromeda Galaxy, which we will inevitably collide with in about 4 billion years, are both spiral galaxies. The Sun is located between the arms, away from the galactic center, and its velocity of movement is approximately equal to the rotation speed of the arms. This positioning allows the solar system to avoid dangerous regions of active star formation where supernovae often occur. It is worth noting that spiral galaxies are often observed beyond galaxy clusters. They differ in the degree of development of their spiral structure, which is denoted by adding letters A, B, or C to the S symbol. Galaxies with A have the main number of stars concentrated in a central bulge, while the central branches of the spiral structure are weakly developed or just indicated. In galaxies with B, the branches are more developed, and for those classified as C, the branches are well developed in galaxies classified as C. The main number of stars is contained in heavily developed and often scattered branches, while the central bulge has relatively small dimensions. The most well-known spiral galaxies include our Milky Way galaxy, the Andromeda Galaxy, and the Bode's Galaxy. An intermediate type between spiral and elliptical galaxies is the lenticular galaxies, classified as S0. In galaxies of this type, there is a bright, highly compressed central bulge that resembles a lens, while the arms are either absent or very weakly traced. Lenticular galaxies primarily consist of old giant stars, giving them a predominantly reddish color. They differ from elliptical galaxies because they have convexity and a thin disk, but they are distinct from type SAR because they lack a spiral structure. The main population of such galaxies comprises old and massive stars, mostly of red and yellow colors. 2/3 of the lenticular galaxies, like elliptical galaxies, do not contain gas, while in 1/3, the gas content is similar to that of spiral galaxies. Consequently, star formation processes, though present, occur at very slow rates. An example of a lenticular galaxy is the Spindle Galaxy in the constellation Draco. More interesting are the so-called irregular galaxies, which do not fit into either the elliptical or spiral categories. Irregular galaxies lack any of the common forms and are usually characterized by chaotic connections, stellar clusters, and sometimes lack a distinct shape or pronounced center. They are relatively rare and make up approximately 5% of the total number of known galaxies. The reason why irregular galaxies differ so significantly from their galactic counterparts lies in the likelihood that each of these stellar systems was likely once an elliptical or spiral galaxy, but something disrupted their formation process or structure, leading to their irregular appearance. Such galaxies are mainly divided into two types: those that have some resemblance to a structure, allowing them to be classified into certain sequences of galaxies, and those that do not even have a semblance. There is also a third type known as dwarf irregular galaxies, characterized by a low amount of heavy elements and a large amount of interstellar gas, making them similar to the galaxies of the early universe. Hence, studying this type of irregular galaxies is crucial for understanding the process of galactic evolution. Moreover, in these galaxies, one can observe young, hot stars. They contain a significant amount of dust that blocks much of the light from the stars. It is likely that such galaxies have planets where the sky appears rather modest and dull. Personally, I would not recommend observing them through a telescope. Bright examples of such galaxies are NGC 1427A, or the Magellanic Clouds. As for the galaxies that possess certain characteristics but cannot be categorized into any of the aforementioned classes, they are referred to as peculiar galaxies. Their structural features can vary, such as distorted structures due to interactions with neighboring galaxies, the presence of dust lanes, ejections of matter, and so on. A classic example of a peculiar galaxy is the radio galaxy NGC 5128.